Hello, everyone. This is part three on climate change. Previously, we talked about the periods of uh, cooling and periods of warm climate. And we see that the ratio O18 over O16 changes. So now we're going to be able to use those isotopes to tell us about the climate. But we use a notation called delta that give us an idea about how is our values compared to a standard. Before we get to delta for oxygen, let's give you this example of percent error to help you understand the reason why we use delta. What is percent error? Percent error is comparing the measured value to a standard or actual value. And how do you find that? We find that by using this equation. Percent error equals measured minus standard divided by standard times 100. You multiply by 100 just to get a percentage because sometimes you get 0.2. It's better to change it to a percentage because it makes more sense. 0.2 as opposed to 20%, it's much better. We say 20 units out of 100. If you look at this example, let's say, for example, we're measuring the length of an object, and the exact value of that length is, sorry, is 200 centimeters. That's the exact value. It's also called, let's say, standard. Student number one measured that length and he find 18 centimeter. Another student find 20 centimeters. We would need to know how far is student number one away from the standard value. And also we would like to know how far away student number two is from the actual value. To do this, we're going to use this formula of percent error. How much percentage of error is for student number one and for student number two. So we're going to apply the equation. Here we say measured minus standards. So measured here is 18 right here, minus 20, which is standard right here, 20 standard, divide by standard, divide by 20, 18 minus 20 over 20. Centimeter cancel each other, and we have minus so 18 minus, I think I make a mistake there. So 18 minus 20 is minus 2. Minus 2 times 100 would be, I'm sorry, one second, what I'm talking about. So let's do it here. So 18 minus 20 is minus 2 divided by 20 times 100. And that would be 0.1. That is correct. So if you subtract these two numbers here, you get a minus 2, divide by 20, multiply 100, you get minus 0.1, which gives you minus 10%. Same thing apply to that student right here. 22 is the measured value right here, minus standard divided by standard times 100, and gives you plus 10%. What does it mean? It means that this student right here has a negative 10% error, means it's 10% lower than the actual value, and plus 10% is plus 10% more or higher than the actual value. So imagine, for example, another student find exactly 20. Let's say student number three find measured is 20. And we would like to know, so he get exact number, 20 and 20, the same. In this case, the percent error for that student who get 20 centimeter is 20 minus 20 over 20 is 0. 20 minus 20 is 0. 0 over 20 is 0. 0 times 100 is 0. 0%, which means that student make no mistake. Percent error of that student is 0 because it gets exactly 20 centimeter. Again, I forget to add this here. Student number three has a measured value of 20 centimeter. 20 minus 20 is 0 times 100 is 0. So that student has made zero error. So the higher the value here, whether it's negative, positive, the higher number, the more error you have. The less number, the accurate you use your measurement. And scientists, they use this for their experiment. They try to find out if their experiment is very far away from the standard or close to standard. For example, if you get 2%, for example, here, that's pretty good because you're very close. You have only 2% error. But if you get, for example, here, let's say 90% error, that's really bad. This means there's a huge problem in your experimentation. But this is just to give you an idea about what is exactly mean by percent error. But here we use the same thing, but not percent error. We use something different. So this delta here as this percent error compare the measurement of students to the actual value. Same thing here. Delta O 18 compare the sample's isotope, the sample we're measuring, like for example here, this side measuring here, to a standard. A standard in this case would be, for example, 20. So what is the equation in this case? The same thing that a percent error with a little difference. So delta sample um, is equal to a ratio sample minus ratio of the standard divided by ratio of the standard times 1000. So let's apply here. The ratio is one. This is ratio, by the way. R means O18 over O16. So delta O18 is equal to O18 divided by O16 of the sample we analyze. In this example here, the analogy here would be, for example, the side, instead of ratio, the side of the measured side here, minus O18 over O16 of the standard, in this case, the standard length here. I'm trying to give you guys the analogy to understand how this is analog to this one, although they are not the same at all. Percent error and delta O are completely different, but the idea is almost the same. Divide by the standard, O18 over 16 standard, times 1000. Why 1000? Because usually the numbers you got here are very small. It's not like 0.2%, it's not, for example, 0.2 or 0.5. It's usually 0.0005. In this case, instead of multiplying 100, you multiply by 1000. In this case, the result would be per thousand or per mil. I'm going to show you the notation here. It's called per mil, and this percent, this one is per mil. Why percent here? Because out of 100. Why per mil? Because mil means 1,000, per thousand. So the standard here we use is called standard mean ocean water. So the O18 over O16 of the standard means the O18 of O16 of the standard mean ocean water. It's the international reference standard for comparing isotope ratio in water, especially for O18 and delta D also. Anyway, don't worry, we'll go over a couple of sample questions and you'll be able to understand how to find delta O. For example, you're asked to find delta O18 and interpret the climate signal. So step number one, use the formula. So the formula is given to you guys here. Delta O18 is equal ratio of the sample minus ratio of the water. Okay, remember here small means standard main ocean water. That's what it calls SMO. Okay. So this SMO here is standard main ocean water divided by ratio of the standard again times 1000. So because you multiply by 1000, we call the result, the unit for the result is per mil. And that's the symbol for per mil. So step number two, substitute the values. If you will be given the ratio of the sample, you'll be given the ratio of the standard, and then you substitute the values, and the step number three, interpret the result. And that's what you have to remember. If you have higher O18, delta O18, remember this, by the way, this, let me just write this down here to clarify things here for you guys. Um, trying to get a pen. Okay. So remember, in cold times, let me go here, cold. Remember, in the ocean you have more of O18. Okay, we have a loss of O18. Why? Because O18 cannot go up, cannot evaporate. So from this, I can write my ratio O18 over O16. Remember, when this goes up, the ratio also goes up. And because this ratio, this water here, this O18 would be incorporated into the shell of the marine living things. So the shell will have a high O18 over O16. And because this is proportional to delta O18 right here, which is this one right here, it's proportional to this O18 over 16. If this goes up, this one also, this goes up. It's higher also. So higher delta O18 in marine shell, like in this example, means cooling. Remember, this is where cooling happens because the O18 cannot go up. It stays there. And because it stays there, O18 increase, the ratio increase, this also increase. Very simple. In warm, let me change the color here for this one here. In warm water, so let me draw here again my. So you remember the here, because this O16 is the one that goes up here and goes all the way, and finally when snow falls, the O16 get locked in here. Okay, I'm just repeating what I just talked about previously. So this O16 locked here, remember, we have a loss of O16 because O16 evaporate easily, move up, and get locked in here. During warming, however, this O16 goes back here, okay, to the ocean. This means what? This means that in the ocean, O16, I mean 16, sorry, O16 will increase. And this means what? If I look at the ratio, O18 over O16, if this goes up, remember what happened to R? It goes down. So in this case, during warming time, I gotta remember when this oxygen right here, this O16 rich water would be incorporating to the shell fragment. So the shell fragment would have low O18 over 16O. Why? Low because this is high. When this is high, the ratio is low. So because O18, 16O is lower, this means also delta O18, this one right here, also would become lower. And that's what you have here. Lower delta O18 marine shells means warming. Higher delta O, in this case here in marine shell, means cooling. Very simple. Okay? In the ice is the opposite. So if we're talking about marine shells, this is the two scenarios we have here. Either we have high ratio or lower ratio. Okay? Now, how about ice itself? In cold time, ice has a loss of O16. What does it mean? It means that O18 over O16, if this is higher, the ratio is lower. So in the ice cores, in the ice, the ratio will be lower, and this means we have cold time. And that's what you have here. Lower O18 in ice core means cooling. Why? Because again, we have a loss of O16, and you have a loss of O16, it means the whole ratio is lower. So lower delta O means cooling. Okay? Now, during global time and global warming, we O16 moves away. Means what? Means if ice lose O16 during warming because ice is melting and removing O18 or O16. If you keep removing O16, the ice will end up having less O16. What does it mean in terms of a ratio? It means that O18 over O16, if this goes down, remember, R goes up. And that's what you have here. Higher delta O18 ice core means warming. So just remember those. Hope you'd be able to understand the concept that would help you link between delta O in marine shells with cooling warming and delta O in ice core with cooling warming. So higher delta O in marine shells means cooling, and lower delta O18 in marine shells means warming. Lower delta O18 in ice core means cooling, and higher delta O18 ice core means warming. And again, they go in opposite direction. If you look at this is cooling right here, cooling, cooling. So you have high delta O in marine shell, the opposite, lower value in ice core. In warming, the here we have low delta O18, and this one has high delta O18. So whatever happened in marine shells, the opposite happened in ice core. High delta O in cold time, lower delta O in ice cores. Lower delta O18 in marine shells, higher delta O18 in ice core. Exactly the opposite. Okay? Oh, let me erase. Let me clear the drawings. Okay, great. So now let's try to look at an example. So imagine we find shell fossil. And remember shell, they are made of calcite, CaCO3. This is calcite. And the shell is made of calcite of living things that live in the water. The SMO, the standard main ocean water is given to you. Just remember the example I gave you earlier about the ruler. The standard is 20 centimeter. Here the SMO in here is 0.0020052. The sample found has a ratio O18 over O16 to be 0.0020152. The question is, find delta O18 and state whether the results suggest a period of climatic cooling or warming. Here we go, the steps here. Again, step number one, what you should do, you should use the equation, which is delta O18 equals ratio of the sample minus ratio of the SMO, the standard, divided by the ratio of the standard times 1000. Step number two, substitute and compute. So the ratio of the sample is right here. That's a ratio of the sample. In this case, shell fossil is a sample. So you plug this in here when it says, oh, a ratio of the sample right here. You plug it in here. I put in purpose in different colors so you'll be able to follow. Minus standard right here, which is this value right here, 0.02052, divided by the standard, which is the same number, times 1000. When you do this minus this over this times 1000, you get minus 24.94 per mil. That's that's how I pronounce per mil. Okay, which means per thousands instead of percent. It should be per thousand. So interpreting the results, now we have negative 24.94. What does it mean? It means simply we have a cold climate. Again, just to put again things in context, why this shows me cold climate. Again, remember, in cold climate, I'm gonna draw the ocean here again. O16 is able to escape, but O18 stays here. It's heavy. And because O18 is heavy, what you got, we got more O18 in the water, which means, I'm sorry, what is this the same question here? It seems like I moved probably, I moved one. Let me just, uh, go up. I think what I did is that I moved to the next slide without being aware that I moved to the next slide, and I'm wondering how we get negative, but it should be positive. Sorry again. Let's go back to this. Okay, so again, here we have the first example shell, which is made of calcite. So we have small, we have sample shell ratio. Again, you substitute first. That's the equation first. You write the equation first. You substitute the value of the ratio right here, this number, minus small right here. You plug in here small, small. So this is the value for the standard times the 1000. And you get the value delta O18, which is plus 4.99. Now let me explain now. That's what I'm trying to explain. When I see a negative number, I say it's not right. There's a problem. Anyway, so it's very simple. So again, all you have to do is plug your values into the right variable, and you'll be able to get to your delta O. So this is the ocean. As I said, in cold times, the only one, one that moves up easily is O16. But here we have, it stays here, we have L18 more because it stays there. So O18 increase. So let's look at the ratio. What happens to the ratio? The ratio, which is equal to O18 over 16O. If this goes up, remember the ratio also goes up. So because O18 is incorporated into the shell here, shell in the water right here. So shell would exhibit the ratio that is higher, that is positive or higher. And because this is positive and higher than zero, more than this value right here, which is the one of the water, it's higher than it. This means that this ocean is enriched in O18, which means it must be cold time. Anytime you have a positive number here of O18, this means you have this O18 over 16 that is higher. Why? Because again, we have more O18 here because O16 goes away, evaporate easily. O18 stays here. More O18 means more ratio. More ratio means more delta 18O. And because we have this value is positive, we can clearly say that this time corresponds to a cooler ocean. This means that shell we analyze here lived in time when we have cold climate, cold ocean. Another example. So let's clear this out and move to the next. Now let's look at the ice core. So I give you an example of shell. Now let's give you an example of ice core. So small, again, same thing. Small or standard for sea main ocean water is this value right here in blue, right here. The ice core is this value right here. So basically, scientists they drill all the way down and they get the ice core and they analyze this oxygen isotopes in them. And the question asks you compute delta O18 and state whether the result suggests a period of climatic cooling or warming. Again, same thing. Use your formula. That's step number one. Write the equation, then substitute the value. So we have sample here, put the value here. The small, the standard, put the value here. You compute everything and you get minus 24.94 per mil. And what this tells you, it tells you you have cold climate also. Why is that? Let me again explain here on the side why. So here we have the ocean right here. So in cold times, again, O16 evaporate easily. Okay, this clouds move all the way here, snow. So we have ice here, and this ice would have also higher O16. Now, how about the ratio? The ratio, which is equal to O18, always you start with the heavy over the light. So because this goes up, what happens to the ratio? The whole ratio will go down, which means it will be negative, lower than the standard. Anytime this is lower, means that it's colder. And you can see here, look at the number here. The number is very low. And because it's low, it means it's cold climate. Okay? So again, this is an easy task. And let's look at other. And this is your turn. Example number 3. Shell interglacial or warming. So basically you have the standard, we have sample of the shell, we have the values here. All you have to do is substitute the values and see what you get. The result is, I'm sorry, this is so this is shell, the exam for shell. You have to do it yourself. If you have a question, you can email me, you can talk to me. I'll be able to help you out with this if you have a problem with this one. Another example 3, ice core, and you'll be able to find easily the value of delta O18. So now if you look at, this is the ice core we got from, scientists got from Antarctica, and the core they got goes from 800,000 years all the way to today. And so this here shows you delta O18 per mil, and you can see the numbers right here. And so higher delta O18 is right here from the highest, or the higher value would be this. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So we have high delta O. And this high delta O in ice, remember, means glacial periods. Let me again explain why high delta O means glacial period, cooling period. So this, for example, here we have cooling here, we have cooling here, cooling time, cooling here, right here, cooling right here, cooling right here, right here, and right here, and right here, for example. So this is high values right here means glacial period. Why again? Because remember, during cool time, the ice has higher O16, which means in terms of ratio, O18 over 16O, because this is high, the whole thing is low. So, um, so delta, this O16 gets higher. This means the whole ratio goes down. So, sorry here, it's a mistake here. It should be lower. Delta O18 means glacier periods. And higher value right here, higher value here means interglacier or warming time. Warming. Okay? So this is anytime we have higher value right here, it means it's warming. Anytime we have lower value, it means glacier periods. And again, you can see here the reason why. Because in cold weather, we have cold climate, we have higher O16, which means the ratio is lower, and it means you have cold periods. Okay, so lower here represents cooling time, and the peaks right here represents warming time. So cycle occur roughly every how many years? So if you count how many in how many years, basically, if I look at, for example, two cool time, for example, this one and this one, for example, the cycle between one cold time, one cycle, another cycle, it's about 1,000 years, approximately. So between each cycle, we have 1,000 years. This shows climate oscillation driven by orbital Milankovitch cycle. Again, remember, as I said when I talked about CH4, CO2, this up and down is caused by natural causes, like the eccentricity or the axis of the tilt of the Earth, and so on and so on. And this caused like the climate to be either cooler or warmer. And you have about eight cycles. uh, ice age warming. We have about eight cycles in here. Okay. So let me clear this out. And this will be the end of our part 3. And I hope you understand how to use those isotopes to find the whether we have global cooling or global warming. Thank you.